So now we're going to be looking at Unit 2, Lesson 6, Practice Problems. So the first thing that we have is that a car is traveling at a constant speed, and the equation for that constant speed is d equals 65t. D represents the distance, and t is the time in hours. So they're asking, what does the 65 tell us in this situation? Well, the 65 we can see is multiplied by the number of hours, which finally gives us the distance. So that means that the 65 is the number of miles traveled in 1 hour. How many miles does the car travel in 1.5 hours? So while I realize that you'll probably be inclined to simply go ahead and do the math, you really should get in the habit of using that equation. So the equation is, well, the equation that's given. So the equation is d equals 65t. I'm going to put a semicolon here to separate. They tell us the time. So that means they're giving us the t equals 1.5. So now every time I see a t, I'm going to substitute in. So d is equal to 65. It should be, okay, I'm just going to, why don't I do this instead? Sorry about that. So d equals 65 times 1.5. And like I've said before, take out that calculator, do 65 times 1.5, and you should get 97.5 miles. And then it asks, how long does it take the car to travel 26 miles? So again, like I said, write down the equation that you're going to be using. 65 is d equals 65t. The semicolon to separate. We're getting the distance this time. So this time we're given d equals 26. So that means every time I see a d, I'm going to write 26. So that means 26 equals 65t. As you should recall, every time a number is next to a variable, it means they're multiplied together. In order to get that variable by itself, we're going to divide both sides by that number, which is 65. These two 65s cancel, and I'm left with t equals 26 divided by 65, not 25, sorry. 26 divided by 65. And if I use my calculator, I should get 0.4 hours. That can also be represented in a fraction form as 2/5 of an hour. Or if you really are interested in the minutes, it should be 24 minutes. But like I said, if you use that calculator, you're going to end up with this as your answer. Next, Elena has some bottles of water. Each of them holds 17 fluid ounces. Write an equation that relates the number of bottles of water B to the total volume of water. So, we've got two ways to write this because we've got B and W. And I'm back. I'm sure you noticed I had to stop because my dog was barking. But anyway, here we are. We're still looking at B and W. And we know, let's first of all do our let statements. We say let B equal the number of bottles of water, and we're going to let W equal the volume of water in fluid ounces. And therefore, we're now writing an equation. We know each bottle holds 17 fluid ounces. So why don't we start out by saying that the total volume of water, W, is going to be equal to the number of bottles times 17. So it would be 17B. So there is one equation. You only have to write one, but I just want you to be familiar with both of them. The other way of looking at this is to figure out the number of bottles B. I would take that total volume of water and divide it by the 17 ounces in each bottle. Or the other way to write that would be B is equal to 1/17 W. They mean the same thing. I'm guessing more than likely you would write the first, but they do mean the same thing. So now for this particular problem, they're asking us how much water is in 51 bottles. So they've given us B. So the easier way to do this would be to use that first equation of water, the total number of water, is equal to 17B. I'm going to write my semicolon because I've been given the fact that B is equal to 51. I'm going to substitute in every time I see the variable B. So W equals 17 times 51. And if you multiply those together, you should get that W is equal to 867, and that is in fluid ounces of water. And then the last part, how many bottles hold 51 fluid ounces? So for this particular problem, I'm looking at how many bottles, so I'm going to start out with that other equation that I wrote where B is equal to W divided by 17. I know that W is equal to 51. So therefore, I'm going to find out that B is equal to 51 divided by 17. Hopefully you know your times tables to get up to there, but if you don't, and you do 51 divided by 17, you'll find out that B is equal to 3, because 3 times 17 is 51. So that's 3 bottles of water. Our next problem is telling us that there is about 1.6 kilometers in 1 mile. They're giving us basically our let statements. X is the distance measured in kilometers, and Y is the same distance measured in miles. Right? Two equations that relate this distance in kilometers and the same distance measured in miles. So, if I start out writing those let statements that we want to get into the habit of doing, right? I don't want to write in highlighter. Go back to my pen, and we will say let the first variable they give us is X equal the distance in kilometers, and then let Y equal the same distance in miles. So now two equations. They're both going to be using x, y, and that 1.61. So if I start out with x, I know that x is the distance in kilometers, and I would be multiplying 1.61 times 1.61 times the distance in miles. So to get x, the distance in kilometers, I would multiply that times y. So that's one equation. The other one means that I have y. And the opposite of that would be x divided by 1.61. Or, if you actually, like we've been talking about this, y is equal to 1 over 1.61 x. And if you actually did that math of 1 divided by 1.61, you would end up with y equals 0.62 x. So the point here is that any of these would be correct. However, the one that I would think you're more likely to come up with would be this first one right here. Next, we are comparing Canadian coins, and those are called toonies. So we're comparing those Canadian coins. We're told that 16 quarters is equal to in value to 2 toonies. And we can see that right here. So, as always, we know that when we go from left to right in our tables, that is multiplication. And when we go from right back to left, that is division. So they show us that 16 times some number is 2. If we're not really sure about what that is, we divide. So we do 2 divided by 16, which is a fraction. We divide it to 1/8. So that means 1 times 1/8 is equal to 1/8. And then 20 times 1/8 remember, we'd still be keeping the top with the top and the bottom with the bottom. That would give me 20 over 8. I would reduce that. 6 goes into 20. 8 goes into 20 2 times. 2 times 8 is 16, so I would have 4 left over. So it's 2 4/8, which I should know I could reduce to 2 1/2. You could have also used a calculator there and come up with 2.5. Either way, still the correct answer. So it's 2.5, or like I had down here, 2 1/2. And then the same thing with 24 times 1/8. 24 times 1/8 means that I'm going to be multiplying and end up with 24 divided by 8, which hopefully you know would be 3. Then they ask us, what does the value next to the 1 mean? Meaning this line right here. And by this point, you should be considering that when you have a 1 on the left and a number to the right, that you're multiplying 1 times that very same number. So that's telling us that 1/8, first of all, equals the constant of proportionality. But very specifically to this problem, it tells us that 1/4 is equal to 1/8 of a toonie. We've got a number of tables here. Each table represents a proportional relationship. For each one, we're going to fill in the missing parts. And then it tells us to draw a circle around the constant of proportionality. So let's take this first one here. How do we get from 2 to 10? Well, hopefully you know that's multiply times 5. So 5 times 7, this first one here, is 35. 1 times 5 is 5. For this one, I know I'd be dividing because I'm going in the opposite direction. So 15 divided by 5 is 3, and that's what would go right here. When I've got my 1 on my left, I've got my constant of proportionality on the right. So I just circled the constant of proportionality for the first. For the next one, how do I get from 12 to 3? Well, you may not know, so you would divide 3 divided by 12. I would reduce that, and it would become 1/4. So this first one, 20 times 1/4, or basically it's asking you is, what is 1/4 of 20? That would equal 20 over 4, which of course would be 5. Next one, what number times 1/4 would give us 10? So it would be 10 divided by 1/4, because don't forget we're going in the other direction. So now I keep the first, flip the second, now we multiply. Well, 10 times 4, of course, is 40. And that makes sense because 1/4 of 40 is 10. My last one, I already know what my constant of proportionality is. It's right there, 1 on the left, constant of proportionality on the right, and I circle it. My last one says to me, how do I get from 5 to 3? Well, I don't know, but I do know that if I divide 3 divided by 5, that will tell me. And now I need to just multiply everything by 3/5 because that's a fraction and it's already reduced. So I've got 10 times 3/5. Put that over 1. That equals 30 over 5. 30 divided by 5 is 6. So I'm going to have a 6 for this first one right here. For the 18, oh, I don't want to circle that. For 18, I'll put this one up here. I have to do 18 divided by 3/5. Of course, I'm going to keep the first, flip the second. Now we multiply. Top with the top and the bottom with the bottom. 18 times 5. Well, 1 times 5, or that 10 times 5 is 50. 8 times 5 is 40. So that would give me 90 over 3. If I reduce that, or basically divide 90 divided by 3, I am going to get 30. And then this one I am multiplying from left to right. I know my constant of proportionality is 3/5. So this answer is 3/5. And then they ask me to circle the constant of proportionality, and there it is. This last one. Describe some things you could notice about two polygons that would help you decide that they are not scaled copies. Well, this is a little bit of a throwback, if you will, from our last unit on scaled copies, but there's many reasons you can come up with, but let's do some of the obvious. We would say they're not the same shape. You know, if they're obviously not the same shape. That should be an A. Obviously not the same shape, like a square and a rectangle, a square and a triangle, a circle and a triangle, those kinds of things. The next thing, if there are distortions from one to the next. Another thing, different sized angles. So maybe there are two triangles, but they're clearly, one has very large one angle, and the other triangle has all equal angles in its triangle. Another way to tell would be that there's more than one scale factor when we compare the corresponding sides. So that's just a few of the ways. You might have come up with a different one, which if you want to come and check with me, you can. But I think these are the basic and most obvious.